Hi everybody, this is the video for section 10.3, which is on chords. So remember in section 10.1 you learned about circles. Okay, we learned the vocabulary: circle, center, radius, chord, diameter, secant, tangent, and common tangents. And we learned how to determine if a line is tangent to a circle, okay, and if it's perpendicular to a radius, and how to calculate the length of the radii in tangent segments. Remember the theorem about ice cream cones. So in section 2, you learned the vocabulary of arcs. So we've had circles and we've had arcs. So there was major arc, minor arc, semicircle, and how to determine if an arc is major and minor, and how to write their labels, how to find the measures of arcs, and what makes arcs and circles congruent. Okay. In section 10.3, you're going to learn about chords, how to use them to find the measure of an arc. So we're going back and borrowing on what we learned in section 2, and we're going to learn 4 theorems about chords. So the first thing to remember is a chord is a segment with endpoints on a circle. So you definitely need to remember that. Okay. So here are some chords, and they're different types. So we have 2 circles here, and the one on the left, we have a diameter. And a diameter actually is a special kind of chord, and it cuts the circle into 2 semicircles. Okay. And so just remember that a diameter is a chord because it cuts through the circle and its endpoints are on the circle. Okay. So on the right, we have 2 types of arcs. We have a major arc and a minor arc. And if you have a chord that's not the diameter, okay, you're going to have a smaller arc, which we call the minor arc, and then we have the larger arc, which is called the major arc. Okay, so minor arc and major arc. Okay, when you have a chord that's a diameter, you don't have a major arc and a minor arc because both of the semicircles, they're the same. Okay, there's no major and minor. Okay, here's our first theorem. Now, the theorems in this section we have to read a little bit carefully. So, let's read this first section. In the same circle or congruent circles. So this theorem is going to work whether or not if in both cases where you have the same circle, okay, or you have 2 circles that are congruent. Okay, and the theorem will work both ways. So the first part of the theorem says if 2 chords are congruent, okay, and here we have 2 chords, A, B, and C, D, and we're given that they're congruent by those little marks, then their minor arcs are also congruent. It means they have the same number of degrees. Okay, their minor arcs are also going to be congruent. Okay, so that's pretty powerful. So it also works the other way. Okay, if you're given that 2 minor arcs are congruent, so here's your minor arc, here's your minor arc, and you're told that those 2 arcs are congruent, then you know that their chords are congruent. So it works both ways. There's a very big relationship between arcs and their chords. Okay, so if you have 2 chords that are equal to each other, their arcs are congruent and vice versa. So let's look at the example. In the diagram, circle P is congruent to circle Q. Okay, so we have 2 congruent circles, so this theorem will apply. And we're given that FG is congruent to JK, so FG is congruent to JK. So we're given that we have 2 chords are congruent. Okay, so we're looking at that sentence. So if two chords are congruent, then their minor arcs are congruent. Then we're given that arc JK, do that in another color, arc JK is equal to 80 degrees. So, and they want us to find arc FG. So, we have two congruent circles. Their two chords are congruent, so their minor arcs are congruent. And FG and GK are the minor arcs, so the measure of arc FG has to be equal to 80 degrees. Okay? So let's go on. So here we have the same statement again, and we're going to do a couple more examples with it. So example 1, oops. Example 1, okay, we're given if the measure of angle of arc AB, so here's arc AB, okay, is 110 degrees, okay, they want us to find BC. So we go to our handy-dandy theorem 10.3, and if we look at the photo, we're given that these two chords are congruent. So we have the same circle, okay, because we're looking at the same circle, just one circle. If two chords are congruent, then their minor arcs are congruent. So obviously the minor arc of AB is 110, so the measure of the arc that uses the chord BC, that also has to be 110. So measure of ABC is equal to 110. Okay, let's do the second one. Again, we're working on the same circle. Now, if the measure of angle AC, arc AC, okay, the measure of arc AC, okay, is 150 degrees, then they want us to find the measure of the arc AB. Okay, so now we have to remember how many degrees are in the whole circle. Remember, that's 360. So in order to find a major arc, which is what arc AC is, okay, we start out with a 360, and then we're going to subtract the measure of AB and the measure of BC. Now, it turns out, because their chords are congruent, the minor arcs are congruent, so this is actually 360 minus 2 times the measure of AB. Okay. So I just realized I set that up wrong, and so I'm going to redo it. Either have to do that or have to go back and redo the whole video, which I don't want to do. Okay, so 360 is the sum of all the degrees in the circle. So 360 degrees, the whole circle is equal to what we're given, which is this 150 degrees, plus the measure of arc AB plus the measure of arc BC. And because these two chords are congruent, that means their minor arcs are congruent, so we know that actually we can rewrite this equation as 150 degrees plus 2 times the measure of arc AB, either way. So 360 minus 150 is 210 equals 2 times the measure of arc BA. So 105 equals the measure of arc BA. Okay, so the margin of arc BA is 105 degrees. Okay, so this would be 150, this arc would be 105, and so would this arc. Okay, sorry for the confusion there, but hopefully that makes it more clear than the direction that I was going. Okay. So we have something handy called bisecting arcs. And so if we have our circle and we're given that arc XY is congruent to arc YZ, and we have our little hash marks there, then the point Y, okay, in any line, segment, or ray that contains Y bisects XYZ, this whole arc here. Okay, so where that comes in handy is when you look at, I'm going to erase this for a second. I'm going to change colors. When you look at these angles, so if these arcs are congruent, then that line also bisects these two angles. Okay, so these angles also have to be, so angle XCY is congruent to angle YCZ. Okay, and you'll find in proving theorems and doing homework questions, this little fact might come in very handy. So make sure you remember that one. Okay, now we're going to go to our theorem 10.4. So this one's a little tricky to understand. So if one chord is a perpendicular bisector of another chord. So here we have a chord. Okay. Now, if we have a perpendicular bisector of this chord, we know that this perpendicular bisector is going to intersect, okay, in the middle of this chord. So this side is going to be congruent to that side. Okay. And we also know, since it's perpendicular, okay, that this angle is going to be 90 degrees. All those four angles are going to be 90 degrees. And if we draw that out and make it a chord, sorry for my squiggly line, it turns out that this has to be a diameter. Has to be the diameter. Okay, so again, if we drew a chord, okay, and we found the middle point of that chord, which bisected the chord into two equal lengths, okay, here and here, and then we drew a line that was perpendicular to that chord, then that line would have to be the bisector. Okay, so let's look at an example of that in action. Oh, okay, we're going to do 10.5 first. That's okay. So 10.5 said, it's very similar. It says, if the diameter of a circle is perpendicular to a chord, to any chord, okay? So I'm going to draw a chord, say from here to here. Oh, come on. Okay. So the diameter then will bisect the chord. So it means that these two sides are going to be, these two lengths are going to be equal, and its arc. So this arc is going to be congruent to this arc. Okay. Now, let's go through that again, because sometimes it's hard to see that the first time. And you can always replay the video if you want to. So, if a diameter of a circle, here's my diameter, okay, is perpendicular to a chord. So the chord, okay, let's do a big chord. Okay, and it's perpendicular to a chord, so this is 90 degrees, this is 90 degrees, this is 90 degrees, this is 90 degrees. Okay, they're perpendicular. Then the diameter bisects the chord. Okay, the chord is actually split in half by the diameter, and it bisects the arc. So the arc for that chord is actually cut in half by this diameter. Okay, so let's work with these a little bit, and hopefully they'll be a little bit more understandable. So here's a nice problem. So use the diagram of circle E, okay, here's circle E, to find the length of AC. So we're looking for AC, this whole AC. Okay, and tell what theorem you would use to do that. The paper's right here. So here are the three theorems that we have learned. Okay, we have 10.3, 10.4, and 10.5. So this is just like what you would see on a paper that you had in the exam if you had a theorem sheet. Okay, so you'd be looking at these three theorems and going, oh, okay, which one do I use? So let's go through that process of thinking. So theorem 10.3 says, in the same circle or congruent circles, two minor arcs are congruent if and if their corresponding chords are congruent. But we're really not talking about arcs and congruency to chords and stuff like that. So it doesn't look like 10.3 is going to help us out. So theorem 10.4 says, if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Well, okay, we know they're perpendicular. Okay, that's what that little red box tells us. But we have no idea if it's a bisector. We don't know that. We're not told that this side is equal to this side. Okay, we don't know that for sure, at least not yet. Okay, so that one goes. So let me get rid of these little guys. So let's look at 10.5. If the diameter of a circle, okay, and here we have a diameter, clearly a diameter, it goes through the center and it has endpoints on the circle. That's the definition of a diameter. So if a diameter is perpendicular to a chord, and here we have the chord, and here we are, it says that it's perpendicular. Okay, so far so good. Then the diameter bisects the chord in its arc. So the diameter bisects the chord in its arc. And this tells us that this half of the chord is 7. So if this is a bisector, then this has to be 7 also. Okay, so the length of AC is equal to 7. Oops, sorry, AF. AF is equal to 7, and we know FC is equal to 7. So the length of AC is equal to 7 plus 7 equals 14. Okay, so we successfully used this theorem to answer this question. Okay, we didn't try to use 3 and we didn't try to use 4 because they didn't work. Okay, so that's how you have to go through, and when you have a problem where it's asking you to find a theorem, you have to go through them and decide which one fits. Okay, and this one's going to do similar. Okay, so find the measure of the indicated arc in the diagram. So number 3 asks for arc CD. Okay, so arc CD. And we're given that it's equal to 9x. So it looks like what we need to find is x. So how are we going to find that? So 10.3 isn't going to help because that's about arcs and all that kind of stuff. Same circle, two minor arcs are congruent. We don't know anything about minor arcs at this point. 10.4, if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. We know that this chord is perpendicular to the diameter, but we do not know if it's a bisector. We're not given that information, so this guy's not going to work. So again, just like in the previous example, if the diameter of a circle is perpendicular to a chord, then the diameter bisects the chord. These two are going to be equal, and its arc. So this arc is going to be congruent to this arc. And now we can set up our equation. It says 9x is equal to 80 minus x. Okay, we're going to add x to both sides. We get 10x equals 80, and obviously x is equal to 10. Okay, so then it asks, what is, okay, so x is equal to 10, right? So, but CD is equal to 9x, so it's equal to 72. So 9x equals 72 degrees. Remember to do that second part, okay? So the theorem told us that CD and DE are congruent, so DE has to also be equal to 72 degrees, okay, because it bisected the arc. Now, CE, let me erase all the chicken scratch. Okay, CE would be this arc. Okay. And so the whole CE is going to be, this is 72, and this one equals 72. Remember, because they bisected? So CE is going to be equal to 72 plus 72 is equal to 144 degrees. And you're done. So again, we use this theorem 10.5, which it turns out is actually pretty handy, and you'll be using that one a lot. But we had to go through and we had to analyze and figure out which one it was good to use. So we're going to have one more theorem. This is theorem 10.6. So this is the formal statement of 10.6, but I found it a little bit hard to understand. So I rewrote it into these three sentences. So again, we have in our same circle or congruent circles. Okay, so this applies whether we have one circle or we have two circles that are congruent. Okay, now let's look at this first one. If two chords, okay, let's look here, two chords, 1, 2, are equidistant from the center. Okay, so that means that here's our center. Actually, I'm going to change colors. Here's our center. Okay, and the distance from the center to that chord, okay, and this distance is this line right here, okay. If these two lines are the same length, okay, they're both, the chords are the same distance away from that center point, then the chords themselves are going to be congruent. Okay. Now the opposite holds true. The second sentence says, if two chords are congruent, let's look at the circle on the right. So two chords are congruent, then, this is our center point, then we know that they are equidistant from the center. Okay, we know this line is equal to this line. Okay, so we kind of get two theorems in one on this one. So on the first one, if two chords are equidistant from each other, then they are congruent. Equidistant from the center, then they are congruent. If two chords are congruent, like in the circle on the right, then they are equidistant from the center. Okay, so let's see how that one works. Okay, so here we have a nice diagram, and it says in the diagram of circle C, we're given that QR, okay, is equal to ST. Okay, so these are two chords. Okay, so two chords are congruent. So that's what we're starting with, okay? So let's look through our list of theorems. Okay, again, we're not talking about minor arcs, so we're not going to use that one. If one chord is a perpendicular bisector of another chord, that's not what we're working with. Okay, theorem 10.5, if the diameter of a circle is perpendicular to a chord, I don't see any diameters in this problem, so we're not going to use 10.5. So that leaves us 10.6. So in the same or congruent circles, we're working with the same circle, so that's okay. Okay, it's telling us that two chords are congruent. So this part of the theorem tells us if two chords are congruent, then they are equidistant from each other. So what does that tell us on this diagram? So here's our center, okay, and it's telling us that our distance from the center to one chord is equal to the distance between the center and the other chord. Okay, and also notice that these little lines are perpendicular to the chord, so that'll come in handy. But what we're dealing with right now is that these two lines are equal. So by now you can easily set up an equation that says 2x is equal to 5x minus 9. Okay, and you're being asked to find this length of CU. Okay, so obviously we have to solve for x, so let's put the x's all on one side, and I'm going to make them positive, so I'm going to subtract 2x from this side and 2x from this side. I end up with 0. 5 minus 2 is 3x minus 9. I'm going to add 9 to this side, add 9 to this side. 9 is equal to 3x. X is equal to 3. Okay, now it didn't ask us to find x, right? It said find CU. And we know from the diagram CU is equal to 2x. So CU is equal to 2 times 3 equals 6. And we're done. Okay? So it required that you use the right theorem, okay, and then the information from that theorem to solve the problem. Okay, and that's what you'll be doing in the homework questions. Okay, so let's do one more example.